Hello, everyone. Welcome to another episode of Quirkcast. This is your host, Tim.
And I'm Mike.
This is Sahil. Welcome everybody to another exciting episode. So before we get into it, just a few logistical things. If you have any questions or comments, please be sure to put those on the YouTube channel, and we'll get to those during the episode. So let's begin without further ado. So Tim, what is the deal with this dark matter? Like, is the universe more than what I can see, or is there more to the universe than just what you can see with light, or what's going on with that?
Yeah, and I'm sure possibly quite a few of us, you guys listeners have heard of this concept called dark matter, and indeed Sahir is right. It turns out that when we try to do various measurements on the universe to measure the amount of matter, and pretty much matter just means like certain types of energy and momentum in our universe. When
Any type of energy, really.
Yeah, pretty much. Yeah, let's just leave it like that. Pretty much any type
Just
of
energy.
Yeah. It turns out that there is more than meets the eye, and in fact, it's not such an insane idea. I think to concretely answer your question, yes, there is matter that we do not see, and in fact, there's a lot more than you think.
Huh. Well, how do you know that if you can't see it? I thought all astronomy was like seeing things, right? You can only do observations via light. Like, how does that work?
That's a good point. Yeah, as you pointed out, pretty much all of modern astronomy up until very recently, some would argue like up until 2 years ago, has been light-based. We are beings of light. All of the atoms that make up our bodies react very strongly with light. Our eyes, which receive light particles, is the strongest processor in the brain, and so we have a very intimate relationship with light, and we've relied on light a lot to sense things. But the question has always existed: what if there is a type of matter out there that doesn't interact at all with light? If that's true, then literally it could be passing through us right now. There would be no interactions with it because, when I touch someone, the repulsion we feel is actually electromagnetic forces. The atoms are exchanging photons with each other. But if something it's completely insensitive to photons, then it would literally just pass through us like a ghost.
Huh. So are you saying like the sensations that we feel of touching something is due to electromagnetic interactions, which essentially is like interactions involving light? And
Yes.
so because these things don't interact with light, you wouldn't really be able to like sense them because our nerves aren't like built for interacting with these things.
Absolutely not. Yeah. Our atoms aren't built for interacting with these things. It's much deeper than neurons, right?
Yes.
I
Yes.
see.
So in fact,
Go ahead.
even for things that interact with us electromagnetically, like things like muons, now which we now know the sun produces plenty of, we do not feel them. So basically, just because we don't see or necessarily feel something does not mean that they don't exist. I think that's one great lesson from astrophysics or particle physics in general.
Yeah, and one of the great modern lessons I would say is that if it doesn't interact with light, then it really, really doesn't exist to us.
Yeah. So okay. So there's these particles you can't see, doesn't interact with light. Like what's
Well,
the
who's
big
saying
deal?
about particles?
Like, matter. Sorry, my friend. Matter. Dark matter. What's the big deal about this? Why is it important?
Yeah. So basically, there are multiple ways to sort of sense matter in addition to just seeing light, right? The other way of doing it is through their gravity. So in fact, one can argue that gravity is probably one of the greatest sensor. Pretty much nothing can escape gravity. So if something
Gravity is a universal sensor, yeah.
Yeah, so it's sort of the greatest universal sensor, but it's also the trickiest, right? Because light is
The
really
weakest. It's the weakest.
Yes. Yeah, light is pretty easy. You shine a flashlight, you can just see it with your own eyes or detector, through some silicone detector. But for gravity, it's very difficult because, like, generally, I cannot feel the gravitational pull on my fingers or my body. It's very difficult. Even our everyday life experiences tells us that. Even though we feel the Earth, but remember, Earth is enormous. We're talking about like particles coming in here. For something as small as particles, it's very difficult. But at the same time, when these particles gather into great quantities, we can actually detect their effects on galaxies and the overall structure of the universe. We see that there's something more that meets the eye.
Huh. So when you say they gather together, what can you explain a little bit more, Tim? What do you mean they gather together? Or
Yeah, and in fact, it's sort of in a similar vein how ordinary matter gather together. So you can kind of imagine, well, how the sun gathered together, how the planets gather together, and this happens in essence because of gravity. Gravity pulls gas together, and those make stars. And because stars dissipate energy, they gather more and more together. And in a similar vein, when you have matter that's not visible, gravity can also gather them together. So if we imagine there exists matter that we cannot see, gravity will act in some sense in the same way. They will gather these matter together. And when they gather up, it actually affects the structure of the universe in a very real way.
huh? What is this effect that you're talking about?
Yeah, so it turns out that probably one of the most dramatic evidence for dark matter is how clumpy the universe is, pretty much. So of course we experience this level of clumpiness like when we're on Earth. The Earth is a giant hunk of metal mixed with rocks basically, right? And you can imagine the reason it formed is because there were some stars and there was some material here already, and then things collide around and we form planets. So that has to do with,
The technical term is dust, right?
yeah, pretty much just stuff being around. Okay.
Oh.
Now, yeah, and now maybe on surface you didn't think, oh, what does dark matter have to do with this? So dark matter operates at a much grander scale. If you zoom out, not in the size of the solar system. You zoom out to the solar system, to the galaxies, to clusters of galaxies. You look at patterns where those galaxies are, you realize that galaxies aren't just like individual dots that kind of totally move randomly. Galaxies form patterns that are kind of linked in these in a particular way. It is random, but there's some non-trivial statistics about them. It's random in a particular way, and we call these the cosmic web. Basically, they're these structures, and in order to explain them, there has to be something that kind of hold those cosmic webs together. So that's one way to see the dark matter.
Huh? So are you saying there's more stuff in these cluster of galaxies that you can't see relative to what you visibly can see? Is that what you're referring to?
Yeah, I think one way to think
Tim?
about it is like you can imagine that gravity is this force that essentially causes everything to want to clump. There's a universal force in the universe causing everything to want to gather rather than spreading apart. Actually, that just contradicts what I was about to say. In that same vein, okay, well, I'll ignore that point. But if you think about like the Big Bang, right? Like everything, the universe is getting bigger, everything is moving away from each other. Despite that push for everything to move away from each other, gravity causes things to clump, despite that.
Mm-hmm.
So as the canvas stretches and gets bigger, you'll have these clumps that evolve over time of high density as dust, attracts dust, and they clump into rocks, and rocks collide with rocks. Shoot, where was I going with this?
You said that things clump together and that the universe.
Oh, yeah. If you just assume that the matter that interacts with light, meaning the matter that we see with our eyes, if you just assume that that's all that exists, there isn't nearly enough gravity to overcome this repulsion from the Big Bang, it would have been impossible for galaxies to ever form and clump in the first place, or solar systems or anything to clump, unless there's this huge amount of extra stuff that's basically causing the seeds for other stuff to clump into.
Oh, fascinating. So what you're saying is that if this dark matter didn't exist, then galaxies probably would not exist. Like everything would just be kind of going away from each other.
Yes, yeah.
Yes, pretty much. Yeah.
It's dramatic too. It's like not even close.
Yeah. In fact, galaxies will not be stable. The problem is galaxies, like this is another evidence for dark matter, is because galaxies as a disk, just imagine kind of like a frisbee, and they spin and turn around. Like as opposed to a frisbee, galaxies, there's no solid structure that holds the galaxy together, right? And because there's a finite speed limit, the speed of light, right? The whole thing is enormous. It's like I think it's like I can't quite convert the unit. It's like megaparsec, but like millions of light years, I think. Right. So in order for one place to communicate to the other, it takes millions of light years just for that to happen. Right. So there's pretty much no rigidity whatsoever. There's no right for the galaxies to hold that shape and be spinning around in any coherent fashion. So if you do a little calculation, you'll see that galaxy just by themselves cannot spin around like that. They're going to fall apart. They're unstable, highly unstable configuration. So what needs to happen is you need this extra cloud, kind of like a gel, like an amorphous cloud that's much bigger than the galaxy itself, right? To kind of be like the scaffolding, kind of, that kind of puts them in place to some extent.
Like loosely, you can loosely say it's like glue, right? It's like you can show, like through very clear calculations, that our existence requires a glue to like hold us together.
So Tim, I want to ask just to give our listeners an idea of what unstable means. So if this matter didn't exist, and we look at the galaxy rotation, ignoring the expansion of the universe, what does it mean for it to be unstable? Would things fly off? Would it just be like
a
spherical type of shape?
Yeah, exactly. Yeah, it means that tiny perturbations will be amplified. So it literally mean that if some stars just happen to kind of wobble out of the plane, it will wobble out of the plane even more. So the whole thing will just fall apart. It's like imagine you're spinning a disk with no rigid structure. It just everything fly away pretty much. Like it just can't. I can't even imagine what that would be like. There wouldn't even be like a spinning galaxy in the first place. It just wouldn't be.
Oh, does this answer the question of at least this sort of observation answer the question why galaxies rotate in a plane, or why things just rotate in a plane? Or is that not
definitively. You need that. You need dark matter in order for...
Wait, no. That's just minimization of angular momentum, technically, but...
Technically, the simplest physics, why it will rotate in the plane, sure, it's angular momentum and whatnot. But to explain the shape, the distributions of particles, and the velocity distribution, you need the dark
but the
matter.
Flatness is not.
Yeah, like technically you can have other ways, right? Like technically, I mean, you could have something like the solar system spinning around, but you would not get the right. It wouldn't look like a galaxy, basically.
No, I mean, think about it. Like, if you look at the solar system the way it actually looks, the inner planets are like zipping around super fast, and Pluto's like, going much slower. When you look at a galaxy, everything is moving like a sweeping wave, like there's some glue holding it together. And
wow,
that.
So I want to get to an audience question really quickly before we move forward, which is, wait, aren't there lots of things we can't see, like when we make sounds?
Yeah,
we can see them though.
Yeah, I think when we say see, we're talking about loosely. Like imagine if we have supervision.
No. We're talking very strictly. We're talking very strictly. Like what's it like? Sound, like you can see air, because air molecules interact with air molecules, and sound is a wave in air. So if you had sufficiently good optical equipment, you could probably visualize compression waves going through gas, which is sound.
That's true. Yeah, if you have good enough cameras to be able to capture motions that fast, and with some nice laser beams and dust scatter around, yeah, you could potentially see it.
You wouldn't even get dust if you had some good analysis of the spectrum and maximum.
Couldn't you say the same for gravity? Like, I mean, not to derail, but the whole like LIGO experiment for gravity waves, like they used lasers to actually like see gravity. It's kind of off topic, but
it does sound a little, yeah, if you say it that way.
Yeah, in principle, we've had multiple ways to use gravity as an instrument to kind of allows us to see things. So. And indeed, yeah, the structure of the universe, yeah, we're using gravity to basically see dark matter.
How ubiquitous?
Sorry, I was going off.
Oh no, go ahead, Mikey. You finish. I'm about to. So how ubiquitous is this? Is this like just confined to galaxy clusters and like just kind of isolated, or is it like permeating the entire universe, or like, is it a very small fraction of the universe? Like, can we give our listeners the kind of scale of what we're talking about?
How many kilograms per square meter, per cubic meter is it, Tim?
I think there's roughly 1 gram. Oh, I forgot. It's 1 gram or 1 kilogram in the entire volume of the Earth, something like that. I think it's about 1 gram. It's about 1 proton.
Wait, no. Yeah.
It's about 1 proton's worth per cubic centimeter. I think that's about 1 gram for the entire volume of the Earth. And because we don't know what dark matter is, this 1 gram, I don't know what the shape of it looks like. It could be a dot, 1 gram, and it could be like an amorphous blob, 1 gram. But then again, it's there. It's not very much, obviously, but remember, like, this is everywhere. Where you see completely empty space, dark matter's there. Between galaxies where they're basically just pure nothingness for millions and millions of light years, dark matter's there. It's like mind-boggling.
It also streams. Yeah, it also streams. It's like water. So it does have like weird like streaks and streams and little vortices here and there probably.
Yeah, probably.
So yeah, it's hard to predict the exact density, but yeah, on average.
Yeah, I think recently people have proposed what Mikey was saying, like substructure of dark matter. It's very, very difficult to measure because once again, you can't see it. So how do you know? It's like, there are these substructures, but it's definitely interesting.
In all likelihood, it probably has some structure.
I would buy that. I would probably buy that because one of my advisors actually wrote a paper on that. So I would buy that.
Yeah, and I think that's one of the most interesting things about dark matter is that like in the scientific community, we always assume it's something boring. We always assume it's just some particle or it's some blob. Those are basically the two kind of candidates for what it could be, either a particle or a galaxy-sized blob. We can get into why those are the two candidates later, but and that doesn't rule out the fact that it could be more interesting. We're just saying we don't know what it is for now, so let's just paint it with the simplest coarse-grained picture possible. But there's plenty of room for it to be very, very interesting.
So you gave the density of it, but I feel like to give intuition, like, is there more dark matter than there is matter, or is matter dominate the universe relative to dark matter, or matter that we can see rather? Or how do you think about that? It's like 4 times greater. Like, what would you say, estimate wise?
24-3.
Yeah, wait.
24-3?
Dark matter over matter.
Like, so 8-1?
Yeah, right.
Wait, hold on. No, it's like 80% dark matter and 20% ordinary matter.
No. It's 74% dark energy. And
yeah, and 20.
Well, let's.
Wait, hold on.
24% dark matter, 3%. Yeah, I remember this pie chart. 74% dark energy, 24% dark matter,
5%.
3 to 5%, yeah, and then 0.002% radiation. It's
about a factor of 5 to 1, give or take, 4 4 to 6 to 1, like 4 to 1 all the way to 6 to 1, somewhere around that. I think we can be more precise. There's some precise number somewhere.
Yeah.
Right.
But there's a lot
Gotcha.
more.
Yeah. So I guess like why is it so hard to know what this is? Like if I mean, can we not design experiments, or like is it just so elusive, or like what's so difficult about this?
None of our tricks work.
I mean, this is
They
like
all use light.
This is like a Nobel Prize waiting to happen, right? Like, trust me, people have tried to call dibs on the dark matter for ages, decades, basically, right? They've tried pretty much all their tricks up their sleeve, right? They build detectors underground. They build detectors with different types of material. People have tried to look for dark matter in colliders, in different, even in different things we can see, in like different dust, different galaxies, different. Oh boy, the list goes on and on and on. Like
I think that the depressing thing is that a lot of the theories, or a lot of these ideas about what dark matter is and how we could find it, rest on the assumption that it does interact with light, just very, 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 very tiny. If it doesn't interact with light at all, zero, like not at all, then the chances of finding it are almost zero as well.
Yeah. So in fact, I mean, in fact, I know maybe in the general public that there's sort of this conception that, oh, it's like maybe if you don't find it, is it really there? Like one of those situations, like back when Einstein trying to find the ether, like this sort of analogy. And let me just say that this is completely false equivalence. Like, we're not in the same situation, right? Particularly because, in a little bit of history, like when Einstein said the ether is not there, because if the ether is there, the theory doesn't make any sense, right? But here it's different. The theory makes total sense. In fact, like Mikey said, there's no reason for dark matter to have any interaction with light. There's no reason dark matter doesn't care about us, right? Dark matter is just the universe. Dark matter could just be like, well, sorry, dude, like you're not gonna get the Nobel Prize.
Dark matter is really dark.
Yeah, I mean that's the job of the dark matter is just to make the universe. Like, well, I don't care. It's like I'm just here. So like, there's no reason. Like the only reason that we think dark matter is there is because of human. We're like, oh yeah, we've found discovery for so many years now. Here's another one, but we shouldn't have that bias. There's no reason.
Yeah, that's the nightmare scenario for dark matter. Like all scientific hope for finding dark matter rests on the fact that it's maybe not all the way dark. Maybe it's only like 99.99999% dark. But if it's actually 100% dark, then we're never gonna know what it is.
Yeah. And always add you can always add another 9 at the end of the decimal. And that's pretty much the scientific progress we've been making. Yeah. Like how much we have not seen.
I'm starting to think that maybe it just doesn't interact with light at all.
Yeah.
And we're screwed.
I guess like so I remember reading somewhere of how there's certain particles like neutrinos that don't interact with light, and they were able to observe it in like via smashing particles together. Why can't a similar thing be done with dark matter? Or I don't know if that's
but neutrinos do interact with light a little bit.
Oh, do they?
Yeah.
They're not totally dark.
Oh.
That's what gives us hope that maybe dark matter is the same. Maybe it's just like super 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 dark, but not quite 100% dark.
Yeah. Let me just clarify.
So if it.
Oops. Sorry. Let me just clarify a little bit. When Mikey said neutrinos interact with light. Yes, it does, but when we detected them, it's through a very similar vein. Neutrinos interact with some cousins of light, basically, like W bosons and Z bosons. But forget the details. But yeah, precisely because of these reasons, we can see it. So dark matter might be similar, hopefully. But it turns out it definitively we can say it's not already. Dark matter is not like neutrino. That people have tried for years to try to prove this hypothesis, but no, it's not. So I can definitively say that dark matter is not like neutrino, not even close.
is there a explanation like why, like a really simple explanation without going too much in details of why it's not a neutrino definitively?
Because
There's
we
not enough neutrinos.
because well because we've tried, we assumed that it's like neutrino, and we ran many experiments and we didn't find any dark matter. That's pretty much it.
No, I thought he was asking why neutrinos can't account for dark matter.
Oh, there's another story. Yeah, sure. Like yeah, go ahead, Mikey. You can.
Oh, you know, I mean, it's just simple. Yeah, there's not enough of them. I mean, it's some of the dark matter is neutrinos, that's for sure. But there's a lot more than, because we can detect neutrinos, so we know about how many there are, and there's something else on top of that.
Okay. Models that you guys like say that maybe it could be this, but purely speculative.
I'm a blob guy. I think it's a blob.
What does that mean? What does that blob? What does it mean, blob? Like
so if it's like kind of a big heavy particle, then it's kind of like a rock, and you can think about it like a particle. But if it's like a super light particle, then it makes more sense to think of them as kind of like this collective blob that kind of just undulates up and down. And yeah, that's called a lot of people call it axions or super light scalars. Yeah, so those are kind of the two candidates for ideas in physics that give the right behavior that we observe. And yeah, I don't know. When Tim and I were coming up, everyone thought it was like a big heavy particle, and so now I guess we're just going the opposite direction.
No. Actually, it's interesting, Mikey. You brought up this word blob. I think in some papers, people would think almost the complete opposite. I know at least some folks I work with, blob, they refers to a particular type of dark matter, which is kind of like a rock, basically. As things clump more and more together, they call that a blob.
You mean machos?
No, way bigger. Like we're talking about like pretty much like rocks, things that fuse together, bigger and bigger and bigger. But
can't explain dark matter. That's why would people think that? Well,
people like me, for example, we wrote papers on strongly attacking dark matter.
Wait, rocks? Like larger, like that dark matter could be made of?
Macroscopic, yeah. It could be like centimeter large, charging through Earth.
You said larger than planets.
Oh, it could be. Well, planet, yeah, in exceptional cases. I mean,
it's a macho, and that's ruled out, isn't it?
No, there could be a size spectrum. It doesn't have to be all one size.
Okay.
The tail end. Well, but we can probably dedicate like another episode, like an entire hour, just talk about.
You're talking about like quirky dark matter, or?
Well, yeah, there are many. Like the literature is enormous. It's like everyone's calling dibs on the Nobel Prize. There are like hundreds of papers.
Right.
Well, probably
Good
hundreds.
luck with that.
There are like thousands of papers every year. I don't know on various kinds of dark matter, right? Like, yeah.
Low quality dog pile.
So I guess to sum it up for the listener, like what would you like need to see to actually say this is what dark matter is? Like what does that mean? Like how would you know that you've seen dark matter?
I would say like scientists wouldn't be happy unless they see it like interacting with something that like that interacts with light, for example. Yeah. So like as Tim said, like neutrinos we were talking about, they don't interact with light directly, but they talk to light through other things. So if dark matter talks to us at all, it's talking through something else, and finding that bridge, I would say, would leave us satisfied that we found it.
So one question I have about that is like, if you were to hypothetically increase the energy scale of like particle accelerators to be like several orders of magnitude greater than what they are right now, would you be able to, because then gravity would become more important, and then if we make gravity more important or relatively on the same order of magnitude as the other forces by increasing your energy scale, would that allow you to observe dark matter, or like would that allow you to see dark matter more, or I don't know?
They did the calculation, and to reach the point you're talking about would require a collider the size of the solar system.
So not too big. So we got this.
No, but it's true. It's true. So if it's a heavy particle, then the higher energies will allow us to rule out heavier and heavier particles, at least generically. Yeah, so that's the one benefit of blind benefit of increasing the energy.
Yeah, I would say using an accelerator to try to create dark matter is not really the smartest move, because
Hey, you're not a fan of the
because it's
three-pronged
difficult.
approach?
Because it's difficult. I mean, yeah.
Not if it's a wimp.
Yeah, I mean, people say, you know, you can try to accelerate it, but I think honestly, it's not the smartest move. Like, chances are, if dark matter, even if dark matter exists, an accelerator will probably create some cousins of it before it creates dark matter. Like, you see something else before you see dark matter. Like,
Yeah, that's the same thing.
Like, it's a fool's errand to try to create dark
That's even more exciting,
directly.
though.
Yeah, but I would say with excitement, also the prospect is almost less likely in a Bayesian way. It's kind of like, well, it's hard, you know. Huh?
I think I'm a firm believer in dark sectors, so I think dark matter is, I don't know.
Yeah, but you can never discount nature might be more clever than we are. It's like you think you know, but dude.
I don't know. I think people who have been basing everything on making everything like economical, it's been successful for a while, but that, I don't know. There's been some famous failures recently.
Yeah. So as we're wrapping up, I want to ask one more question. So when you had like two massive objects that were colliding with each other, they produced gravitational waves that were able to be detected. Could there be such thing with dark matter, like two huge clumps of dark matter, really, really enormous clumps, like collide together and produce gravitational waves that you could detect or something like that?
Oh, sorry, what do you mean? You mean it makes dark matter or what?
Could you
I
ever
just
detect
mean
dark
like
matter through gravitational waves?
Yeah, something like that, since it interacts gravitationally.
Oh yeah, I mean, people have tried, trust me. People have tried to see if these collisions make dark matter so you can detect them. People have tried to see if supernova makes dark matter so we can also detect them in some ways. I mean, when I was a researcher, we looked for crazy stuff. Maybe like dark matter went to the moon, like it gets stuck on the moon.
Collected.
Yeah, and they're crazy stuff like maybe dark matter can heat up Jupiter. Oh, I guess a dinosaur, of course, is one of the more famous.
Oh yeah.
You know, Lisa Randall. Maybe the dark matter, you know, attracted some asteroid and killed the dinosaurs. So dark matters could be killers. But I mean, the possibility is just incredible. It's just a big unknown. You really don't know.
Yeah. So what I'm getting from this is that dark matter is highly elusive, and we're not able to detect it because our tricks don't work with light, in particular. Is that a fair assessment?
Very sad.
Yeah. So any concluding thoughts that either of you want to say before we head out?
Yeah, well, I just want to say that like scientifically, dark matter is real, pretty much, and when I say that, I say it in sort of like a cautious way, like we know that something is there to hold the universe together, and people can argue on the details on like, hey, how much does that change the rotation of the galaxy? How much does it do A and B slightly differently? Right, like the details we don't know, but like it really is there. But I think a lot of the conflicts or a lot of criticism people have with some of these dark matter models, they occur because people insist on having a particular idea on what dark matter is. So a lot of the criticism on, you might hear like dark matter model is like, hey, what if dark matter is exactly one type of particle with exactly this one type of property? Oh yeah, then maybe it doesn't match with the experiment. But like we, you know, during our discussion, like there's a huge, like basically limitless possibilities. So it's like, well, maybe you just lack the imagination to really think about it, right? So yeah, basically we're like 80% there to list out some of the properties of dark matter, but we just need those 20% left, and be like, hey, really, what is dark matter?
And just for fun, I want to point out that
Yeah.
it's not impossible that dark matter has dark planets and dark people and dark buildings that are like literally just past. Like, that's it's not that crazy. Yeah, I wouldn't bet money on it, but
Yeah, there's always this concept in physics where a new physics theory always have to do something for you. Like, it has to be economic, it has to solve some problems. But like real world, like imagine there were dark people, there's no way they would have expected like real people exist. I mean, to them they'll be the real people. So who's to say there isn't dark civilizations? I mean, maybe we're the dark ones. They're not the dark ones.
we are. I mean, them.
So actually, I just got 2 audience questions. So lightning round, really quickly. Let's try to answer this. So suppose you find dark matter, what can we do with it or benefit? And then how will our world change due to it?
Ooh.
I'll give this to Mikey since you gave a very kind of grimacing look.
The answer is the same as what they said in Particle Fever, and what what's his name said. Who said?
David Kaplan.
I have no idea.
Huh? David Kaplan.
No, that was part of historically. Who said? What when the judge asked, "What is this good for?" and he said, "I have no idea, but I guarantee you'll tax it one day." I don't think they'll ever. I don't think they'll ever tax dark matter. So it's even less useless. Yeah, and yeah, nothing.
Yeah. Well,
right.
That's a tough question. But maybe we can leave it for next time.
Well, okay. Well, if we really found out that there were dark people like sitting next to us, it would explain ghosts, right?
But can we see ghosts? That's a different story. Can we or can we not see ghosts?
The idea that there are like complex life forms that interact like with real energy, literally in a physical close proximity to us, is something that like people have always like felt for a while, or it's an idea that people have been intrigued by, and the idea that there could be something to it has some philosophical significance, I think.
I thought you said that we can't like sense or feel dark matter because it doesn't interact with light, or I'm not sure.
Yeah. But so, it's still in close. It's weird, even though it's so far from us in that sense. It's in a very close, like physical proximity. It's still it can still have the same notion of physical proximity, which is weird.
Yeah, I mean, just to throw it out there, because the possibility is so numerous, it is possible that if you find some ways to interact with dark matter, because there's so much of it, if you can even find some remote way to harness energy from it, it will basically be unlimited, be limitless, right? But that's a far-fetched idea. But
dark fusion.
It would be insane. Yeah, but the real answer is probably nothing. At least for like the foreseeable, I don't know, 1,000 years. Probably absolutely nothing, other than the fact that we understand the universe better.
Unless we find evidence that it has some complicated chemistry, then I think that would be very, very what's the word? Like moving to the world.
And there will definitely be lots of movies. Let's put it that way. Good movies.
So what I'm getting is like pragmatic use is not going to be that much, but Hollywood will take it and make money from it.
Pretty much.
At least it'll be at least as useful as discovering exoplanets, which I think will be useless for even longer. I mean, from a practical standpoint.
Makes sense. Makes sense. Cool. So I think with that, we can end it here. And so I'd like to thank everybody for joining us, and we'll see you all next week.
Yeah, see you all next week. Bye.
See ya.